Lesson 20, scientific notation. So this is just a quick refresher for those of you guys that want to know how to do it. We'll be able to use scientific notation to solve problems. Now, for a lot of you guys, this will be just like, yeah, I've seen this already before. I know this back to front, in which case, good, easy, sit back, relax, and enjoy the dulcet tones of Mr. Greer. If you guys have not seen this before, then pay attention. If you guys struggle with this kind of stuff, then maybe it might be a good chance to read, cover it. Now, we need scientific notation. The reason why we're doing scientific notation that I'm going through with you guys is because this next topic we're going to talk about essentially electrons. And the problem with electrons, when we talk about electrons and groups of electrons, is that we need ways to, as electrons are very, very small. They're like, 9 times 10 to the power of negative 31 kilograms, I believe, is the mass of an electron. Don't ask how I've memorized that, I just have. And they've got a very, very small amount of charge. They've got a very, very small mass. They're very, very small. So therefore, being able, the only way to be able to talk about electrons, it would be to have 0.00 without scientific notation. It would take us this long just to write down like something about the number. And even then, we probably need to throw about another 8 more zeros in there. So we need to have scientific notation so we can actually explain this topic properly, because we're dealing with electrons and moving charge. When we talk about later on, we'll talk about groups of electrons. So you need a lot of electrons just to get to one charge, one unit of charge. If you think of when every time you statically electrocute, statically shock something by touching a doorknob after you rubbed your feet on some carpet, that metal doorknob is going to transfer electrons of the order of millions upon billions upon trillions, quadrillions, quintillions, sextillions of electrons. So being able to talk about that using proper numbers, using scientific notation, is going to be really useful. Before we do this, what did we look at last lesson? Last lesson we talked about the history of electricity, the first electricians, people that worked with electricity were using amber. Now I actually got this wrong last lesson, so this is a bit of a quick heads up. I got it wrong, but yeah, grabbing a look here, we can see that you can see here, here's fur, and where's amber? Amber's here. So amber will gain the electrons, whereas fur will lose the electrons. I think I may have said it the other way around. It gets really confusing because if you look at like something like plastic, and if you look at like paper and glass, and it sort of just gets a bit mixed up. Anyway, 1 second, hold on. The next thing what we did was we looked at the Leyden jar. The Leyden jar was essentially a jar which is a way that we could store large amounts of charge. And then what we did was we talked about the voltage part, which was now a way that we could get access to electrons whenever we wanted. And we talked about what is electricity, and then we wrapped up with how electrons move. And we sort of talked about the main principles of why electrons want to move. And essentially, they want to balance out a charge. Today, we're going to talk about scientific notation. So we're just going to quickly go through some of the main facts about scientific notation. Now, we're going to talk about how much does the planet weigh. 1 second, hold on, I'm just going to check something. So we're going to talk about how much does the planet weigh. So when we talk about how much the planet weighs, we sort of look at the Earth. Let's go look at the Earth. That is a huge number here. We've got, I don't even know how to say that number. If we've got 1,000, million, billion, trillion, quadrillion, quintillion, septillion, hexillion, septillion, we're looking at like 5 octillion kilograms. But even then, what the heck is an octillion? I don't know. That's like, if I just said, oh, I've got 5 octillion kilograms, it'd be a bit difficult to explain. We've got the moon, which is, you know, a huge number as well, and the sun. And one of the issues we've got with all of this is that we've got these really big numbers, but these are really hard to sort of, with these really big numbers, it's really hard to compare them. Now, when I've written them out here, it's actually not too bad because you can sort of see their relative lengths. But if you were like using different fonts, so if you were handwriting these, and if you had some heathen that didn't use commas for every 3 zeros. By the way, I learned recently that that's not a common trait amongst all countries. Some people prefer 3 zeros, some people prefer 2 zeros and 3 zeros, and yeah, not common either. So the question that I usually ask for people is this: what are the important parts about these numbers? And you know what, I'm going to ask this to the chat really quickly. If you look at these numbers, what are the important features of these numbers? Like, I know, I get that they're, or you might even want to ask the question, what is not important? What can we sort of ignore? Is there a way that we can think about these? Ask this to the chat. I want you guys to throw me an answer. It doesn't matter. You can do it privately if you're worried you're going to get it wrong, and I won't expose you. But unless you get the answer right, I'm supposed not to hit that silence person. So what is important about these numbers? There are actually two things. Okay, one answer coming through. One answer is they all have zeros. Yep, that is important. That is something that is true. But what can we? Is there a way that we could have a shortcut to write down the top number? Or the second number? What's some of the shortcuts? What's important about the numbers? How can we memorize these really quickly if we had to? That's one of the ways that I usually test students. I say, can you guys memorize this bottom number? What's important? Come on, guys. Those of you that already know scientific notation really well should be able to tell me what are some of the key things about these numbers. Like, what is a key thing when it comes to, if I asked you to memorize the top number, what would you need to know? They can be defined by powers. Yeah, sure, that's right. Yeah. If I asked you, then I'm going to ask this question again. Think about this question. If I asked you to memorize that top number, what would you do? Make it shorter. How? What is important about the top number? What would you do to memorize it? Look at how many zeros there are. Thank you to GLR. That's exactly what I was looking for. There are two important facts with these numbers that would make it really easy to memorize. The first thing I would do is to count the zeros. Because ultimately that's one of the things here, is that there are a lot of zeros here, but if I just knew, well, I need to know how many zeros there are and put that at the end, then yeah, cool. If I know for this one there is 3, 6, 9, 12, 15, 18, 21 zeros, done. I put that at the end. I've got 3, 6, 9, 12, 15, 18, 21, 24, 27 zeros. So I put that at the end. What's the other important idea then? If one of the important ideas is how many zeros, what's the second most important idea? What else is important with these numbers aside from the number of zeros? If I asked you to memorize this top number, you count how many zeros, what else do you need to know to be able to write the number down? The kilograms, yeah, well, that would be a unit. That's important to know too. But what else is important? Like if I said, if I covered this slide up, you know, if I cover this slide up and I ask you to, if I cover this slide up and I go, okay, cool. Now I want you guys to memorize it. What would it be? Numbers cannot be bigger than 9, so it's like 5.972 times or whatever. Yeah, that's the part that I want you guys to figure out. The other part that's important about these numbers is the first significant digits. If I want to memorize this number, right, all I need to know is that there are 21 zeros and the first digits are 5972. So I could go to a completely brand new slide and go, well, I know that's going to be 5972. And then there was 21 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. That is the same number, because what I did was I memorized how many zeros and this number at the start, which is the significant part. And that's exactly the same thing for this number here. If I memorize the significant part and then the amount of zeros, they're the two things I need to remember. If I memorize the significant part and then these number of zeros, they're the two things I need to remember. That's what I need to know in order to memorize a number. And by knowing these two facts, this compresses this idea into a much smaller idea, a much smaller bite. If I can then use this idea to compare them, if I can say, well, this has got this many zeros, and this has got this many zeros, it allows me to break it down. Guys, you guys have been so you guys have spent so much time memorizing the rules for significant figures. I don't think you understand the importance of significant figures. And that's what I was trying to get with these questions. Why do we have significant figures in the first place? To make these numbers easier to memorize, to read, to understand. And then what do you need to know about them? You need to know what's significant, and then you need to know how many zeros there are. Now, to be a bit more specific, we do a couple of cheats when it comes to these kind of things. We have some ways when we make significant figures, we don't just write down this many zeros in this number. We actually have a formula to do with that. And I'm going to talk about that formula here. And this is what I'm going to talk to you guys about right on this slide. So give me a sec. Whoops. Man. Okay, so that's where I need to go. Whatever. I was trying to erase all of the ink on the slide, but you know, this will work too. So let's have a look at this number here, 52,000. Now 52,000 is actually, in comparison to the ones that we just had, 52,000 is not necessarily a huge number. But we should just remember 52 and 3 zeros. But remembering 52,000 wouldn't be that hard. But what I want to show you guys is this. How do we get rid of the zeros? How do we fix this so it works? So when we do the significant figures, instead of counting the zeros, which is what I said in the previous one, we're gonna count the parts that aren't important. To do that, what we want to do is we need to make a number that is between 1 and 10. Now, the best way to make a number between 1 and 10 is to make, well, in this case, 5.2. That's between 1 and 10. It's more than 1 because it's 5, but it's less than 10. So I don't write 52. That's not right. Even though 52 is significant, the only significant part, instead of writing 52, I write 5.2. And then what I do is I say, well, how many times did I have to move that decimal place to get to there? Well, I know that straight away I have to move it 1, 2, 3, because it's 3 zeros. And then I have to move it one more to get it between the 5 and the 2. So that's 4. 4 times do I have to move it. So then all I need to do to turn this into a scientific notation is to put times 10 to the power of 4. That 4 is the same amount of times that I need to move it. Now, times 10, and you guys should know that if I multiply any number times 10, it will become a bigger number. That's going to become 200. And all I'm doing is adding zeros. So this times 10 to the power of 4 is almost equivalent to the previous slide as saying how many zeros there are. You might say, okay, well, what's the advantage of doing this compared to doing this? The advantage to doing this is if we always put a number between 1 and 10, we can always compare them. I can compare 5.2 times 10 to the negative 4 to 3.6 times 10 to the power of 6. Even though these are different numbers, 3 and 6 and 5 and 2, because I've got the same, because they're roughly the same size, I can easily look at the second digit and say, whoa, this is a lot bigger than this one. In fact, you can almost say this is 10 to the power of 2 larger than the other one, which is, you know, just looking at the orders of magnitude, which is the same as saying how many times 10 it is. So that's how we can create, this is how we create scientific notation. And I guess the point here that I'm doing is the reason that we follow these rules are to simplify it. Ultimately, I've gotten rid of 3 zeros by just replacing it with times 10 to the power 4. If you had 10 zeros, you could replace it with times 10 to the power 10. And the only reason why we make it 5.2 instead of 52 is so that we can compare all numbers. And that's why this is so useful. Let's grab a little bit more. Let's look at some more examples. Now, this guy on the left is a little bit larger. This guy on the left is looks like about 5.1 billion. Yeah, I think this is about 5.1 billion. Or 51 billion, sorry, not 5.1, 51 billion. So how do we do this? The same method. We need to pick a number between 1 and 10. In this case, it's going to be 5.19. The decimal point has to go here. In order to get there, we need to go 3, 6, 9, 10. So times 10 to the power of 10. So I've just compressed all of these zeros into here. Now I have to keep that 0.19, but you know, that's okay. I will point out though that let's just say that you had some ugly number. Let me show you an example where you might use scientific notation but in a different way. Let's say you have this number here. 216,000. Sorry. Now, normally what you would do in this type of number is you'd say, well, you would have something like 2.16701 times 10 to the power of 3, 6, 9, 10, 11 times 10 to the power of 11. But to be completely honest with you, what we would usually do, especially in engineering, is we'd probably do this: 2.17 times 10 to the power of 11. You might say, whoa, you're changing the rules here. But what I'm doing is I'm just saying, well, I'm going to round this to almost like, it's almost the same as rounding it to 2 decimal places. The only difference is I'm not rounding it to 2 decimal places, I'm rounding it to 3 significant figures. Now, normally what I would do in this kind of lessons, I would also spend some time teaching you guys about significant figures, but I've decided not to teach you guys significant figures in this course, just because it's a little bit not necessary. We don't need to know it, but but if you do really want to know it, I'm more than willing to go through with you guys privately at some time. But yeah, this is the idea, is that instead of, I've simplified this number down into 3 numbers, 217, and that's because 216 or 217, these are the most important parts. Ultimately, You might say no one really cares when you're looking at when you're looking at billions. No one really cares about like hundreds of billions. You don't really care about one extra $1 billion or something. You care about the this is an extra 300 million. So it's like 300 million. Whatever. We'll round it up. Doesn't matter too much. If you're looking at a number that's really, really huge, it's like, what's the difference between 2.16 billion or 2.167 billion or 2.1617 billion. It's like we're just rounding it, making the number easier. Let's look at this one here. Write in decimal notation. So this one we're going the opposite way. So we're taking as an idea which is in scientific notation and turning it into our regular decimal notation. So what would that look like? Well, if we move the decimal point to the left when we were trying to turn it out, we're just going to move it to the right. We're just going to go, well, this is times 10 to the power 2, so I'm just going to make it bigger, 713.6. And I know that because I move it once, twice to the right. And that's actually a technique that I use a lot. I usually say, well, this is a times 10 to the power 2. That's a positive number. So that means that then it's going to be positive, means we're going to make the number bigger. So that's going to be bigger number here. Can I get you guys, we've got about 15 minutes, so I would really like you guys to do this quickly. Could I get you guys to put in chat the answers to these bottom two? I'd like you guys to work together or, yeah, whatever, but I want to get through this slide, this PowerPoint with you guys today, so I would really like you guys to work on this quite quickly. What is the left one in scientific notation, and what is the right one expanded? 1 times 10 to the power 4. Yeah, technically, although you're correct there. I would have preferred to be, you know what, Oliver? I'm going to keep that. That's, yeah. So the first one would be either 1.364 times 10 to the power 4, but you know what? Oliver suggested, and I kind of like it, 1 times 10 to the power 4. And that's, pretty much also fine. Like, that's and I'm going to do this. This means approximately equal to. So we rounded it down. And that's the thing, is like, if you were looking at like a population or something, if you were looking at a group of people, you would probably round it down to about, about 10,000 people came to the rally today. It's like, or not exactly. Or you might say 1.4. if you were going to two significant figures times 10 to the power 4. Both of those are pretty good answers, but, either or. The other one here is Ewan's thrown over to us is got 8, 1, 2, 3, 1, 2, and 3. We're making 8 million here. And the reason that we know it's 8 million is because that decimal place needs to get moved 1, 2, 3, 4, 5, 6. And then that's how we get to 8 million there. I can't actually count the amount of zeros because they're very small, but yeah, that's how we make a number larger. So this is what we talk about when we talk about large numbers. This is what we're dealing with here. And I've also had a quick chance to talk to you guys about significant figures. But yeah, beautiful. Let's go. We've got a couple of extra slides left, and I want to get through to this stuff at the end because the rate stuff is actually what half of the stuff is on the new worksheet. So I want to get through that. Now, when you're dealing with numbers that are very, very small, it's the opposite. Okay? So the opposite is true. Again, you still want a number between 1 and 10. In this case, this number between 1 and 10 is 2.5. But to get to 2.5, I have to move the decimal place to the right. I have to move it 1, 2, 3, 4, 5 times to the right. So because I'm moving it the other way, or I need to put times 10 to the power of -5. Now, there is that's how I usually remember these types of things. So I'm just like, okay, I'm just moving it to the right. I honestly go like this. It's a negative. negative power means equals small. So that means if I have to move the decimal point, I'm just going to count how many times I have to move the point. This is a small number, so I'm going to put a negative. That's how I remember that one here. Now with this next one, I'm going to show you two ways to do this one. The first way I'm going to do is the proper way. How you would do this one is writing in decimal notation. You write down 7136, and then you just move that decimal place once, twice, put a 0, 3 times, put a 0, 4 times, put a 0. Put the decimal point, put a 0 here. So that gives you 0.000736. Now I'm going to do, actually I'll keep those in just in case you want to know. Now we're going to do, we're going to show you the, this, which I call the Greer sneaky shortcut. I don't actually call it that, but yeah. What I do with this is I just look at that -4. And I'm like, okay, that means that if you look at this number, right, notice how we have to move this decimal place 3 times because you have to move it once to clear this 7, and then 3 times because there's still 3 left. But if you count, there is the 3 movements, but you've also got the 0 at the front. So there's 4 zeros there, and that's a 4. So my sneaky shortcut's this. I always just go, put 4 zeros, 1, 2, 3, 4, and then I put a point at the first one, and then I write down the number. That's my sneaky shortcut. You just read this, and that's how many zeros you write. So what I want you guys to do in chat is to do this one and this one for me. Convert this one to scientific notation. Convert this one into decimal notation. You can work this out by doing the movement rules, or you can use my sneaky cheat. And the only reason this sneaky cheat works is because we always write down scientific notation as one number and then a point. Otherwise, the sneaky cheat wouldn't work. Unfortunately, the sneaky shortcut doesn't work with positive numbers, which is times 10 to the power of 3, because you don't always know how many numbers are at the end of the number, so you can't always use that cheat. But, you know, whatever, works some of the time. Can I get some answers for the first one? 0.135 in scientific notation is what? .135 in scientific notation is what? Come on, let's go. Let's go, let's go, let's go. (1.35 times 10 to the power -2 is correct. Thank you. 1.35 times 10 to the power -2. Easy, because I have to move this once. Actually, I only have to move that once. So it's only 1 times 10 to the power -1. Yeah, but otherwise, of course, don't stress. What about this next one, guys? Can you give me this next one here? 4.8 times 10 to the power -6 as a decimal number. Okay, let me count to see if you got this correct, Dylan. So we've got 1, 2, 3, 4, 5, 6. Yep, beautiful. So again, using my cheat, I'm going to go times 10 to the power 6. So 1, 2, 3, 4, 5, 6. Put a decimal point here and then write 48. And that's exactly it. Now and going back to that same idea that I initially taught you guys, look at this number here and look at this number here. Now, these, from its first glance, is really quite difficult to see which number is smaller. But if you compare this number here to this number here, it's quite easy to say this one is smaller. This -6 is going to mean this is a lot smaller than the other one. And it's only 10 times smaller, but it's still, you're comparing 48 to 250. That's what we're talking about here. But still, it's a lot easier to compare these lines in green than it is to compare these lines in red. And that's why we use scientific notation. And because it's always one number and then a digit, one number decimal point one number, it's easy to sort of go, oh, okay, even though that's a 2 and that's a 4, I can still look at the number, I can still sort of look at the powers and get a rough idea of what's going on here. And it's just, that's what makes these things really useful. And the decimal, like, you can get just a rough idea, and it makes it really easy to compare. It also, as you can tell, compresses this. If you look at how long this takes up, it compresses that down into a very short amount of space. Especially when you're looking at stuff like 2.16 times 10 to the power of 24. Yeah, you do not want to be writing 22 zeros. That would take you forever to write. So now what I'm going to do is I'm going to move on to this. So pay attention, guys. I'm going to move on to this last slide. I'm going to move on to these last 2 slides now, I think. I'm going to skip over this stuff here, the scientific notation, add and subtractions. I'm going to skip over this, even though it's actually quite interesting. I actually show you guys a quick cheat on how to do that. And then scientific notation, multiply and divide. Mostly the reason I'm skipping over this is because even though I really care about you guys learning and understanding this, getting some of the cheats, because it's really good for your numerical help, ultimately, you guys can just shove these into a calculator and get the answer. I would like to teach you guys how to do this properly, but you guys can just put this into a calculator. So what I'm actually going to do is the very end of this lesson, I know this is the stupidest thing that you guys are ever going to hear. I'm actually going to go back over this slide at the end of this lesson. So if any of you guys want to, waste 5 minutes of your lunchtime listening to me talk about this, you're more than welcome to, but it's not going to be, you don't have to. I'm going to dismiss everyone, and just the ultra nerds can stick around, but if it might just be me going through it by myself. But I want to go through this last bit here because I want to do this before we run out of time, which is rates. Now, this is the second thing that becomes a massive thing about the next couple of lessons we're going to talk about, is we're going to talk about rates. Now, what is a rate? Now, rates allow us to talk how 2 units change. Now, I mostly know a lot about rates because I taught this in year 8, so year 8 maths to students. And rates is actually an interesting sort of thing that students usually get a little bit confused and a little bit wrong. What a rate is it sort of says, it's just how one thing changes with another thing, similar to a ratio. And with ratios, it's just you're comparing one thing to another. With rates, you're comparing 2 things with 2 units, 2 different units. So you might be comparing joules per centimeter. You might be comparing newtons per second, That's what a rate is it talks about how 2 units change. You might look at temperature per day. How does the temperature change every day? Is it a positive change, a negative change? And of course, rates closely linked to our good friend radian, but we're not going to be discussing that today. We're just going to talk about the basics here. Firstly, how can we convert rates? Converting rates is pretty easy to do. 5 minutes left. Here we go. 60 kilometers an hour to meters per second. Okay, so 60 kilometers an hour to meters per second. That's a conversion we can do. Let me show you how to do that. So this kilometers per hour, that slash means that we've got 60 kilometers for every 1 hour. That's what the slash means, is you're dividing it. So I can easily convert 60 kilometers into 60 times 1,000 to turn that into 60,000 kilometers. And 1 hour, well, guess what? 1 hour, if I multiply that by 60 minutes, 60 will give you 60 minutes, times 60 again will be 60 seconds. So that's going to be 60,000 divided by 3,600 seconds. So that's going to, and I can now put this into my calculator, but you can quickly just cancel out some of the zeros here. So 600 divided by 36 is essentially what we've got. And that comes out to be 600 divided by 36 gives us 16.7 meters per second. And that's it. That's the new conversion unit. All I've done here, and there you could memorize, oh, you just divide by 3.6, and you know, a lot of my physics students do that. They just memorize that. But I actually prefer to do this by hand because it makes it very clear what I'm doing, what I'm converting. And especially it's really good because if I then ask students to write down how fast is this moving in centimeters per second, if you don't know the conversion and how to convert it properly, then you're going to be in trouble. Now, I've got a bit here, and I've got about 4 minutes left, so I'm going to put this up here, 24 kilometers per liter. I'm going to give you guys 1 minute to write this down in chat. If you guys don't write this down in the answer in chat, then I'm going to move on. But I've only got 1 minute to spare, so that's all that I'm going to give you guys. Go. If you guys don't give me an answer, that's fine. I will just move on. But yeah, 24 kilometers per liter into centimeters per mil. We've got 86.4. That's not going to be correct. It's because ultimately, with centimeters and milliliters, I can tell you straight away, are measures of just times 10. So, for example, to convert kilometers to centimeters, what have you got to do? So it should be. It shouldn't be a different number. I'm going to move on in about 30 seconds unless anyone's got an answer for me. 24,000. Okay, that looks promising. Let me just check to see if that's correct. So we've got 24 kilometers per 1 liter. Now, how do you do this? You go, well, 24 times 1,000 kilometers times 100 to get it into centimeters. And then for a mil, you've got 1 liter and you multiply that by 1,000 to turn it into milliliters. Guess what? That's going to cancel. So you're going to have 24 times 100, which is going to be 2,400 centimeters per a mil. Perfect. Good job, Leo. Someone else got, no, sorry, you got it wrong. So we've got a couple of extra zeros in Leo's answer. And Dylan got a little bit too high as well. So that's how I got rid of that. And of course, if you just multiply these out and divided them, you still would have got the same answer. Okay, I've got about 2 minutes to go through our very last slide. Oh man, it's going to be a rush. By the way, I'm not even checking if you guys are writing this down as we go because I've been trying to go through them quite quickly. But I'm hoping that you guys have been writing down some of this stuff as we've been going through them. If not, yeah, this is the last slide I'm going to go through with everyone. And then I'm going to dismiss people. But this is about changing rates and using rates to our advantage. And this is going to be my last sort of slide here. We're going to look at this first rate here. The person makes $26 per hour. So let's write this down as $26 for every 1 hour of work. Okay, how much will that person earn in 4 hours? Okay, so how do you use rates to work out questions like this? There is a complicated way that I could show you guys, but the fastest and probably most easiest, there's a complicated way using ratios that I really like, where you go, well, 4 over x over 4 equals 26 over 1, and then you cross multiply and that gives you the answer. But I'm going to show you the fastest and easiest way that most of you guys will probably be using by now anyway. The fastest way to solve a question like this is to say this: 4 hours multiplied by $26 per 1 hour. Now, this might seem really obvious, and I know some of you guys are like, oh my God, this is like going back to year 8. I know this stuff back to front. But it's really good to just look at this from a bit of a outsider perspective, and also just get, because ultimately this is going to help us when we do more complicated things with things that aren't as obvious as these rates. But what I like to think about is this: is you're multiplying by hours and then you're dividing by hours. So that's like canceling that out pretty much. So that means you can have 4 times 26, and 4 times 26 is going to be $104. And I know that it's dollars because ultimately it's dollars divided by hours, but the hours have been cancelled out. So it's just dollars. Now, how much will they earn in 1 hour? Well, guess what? That's even easier. 1 hour multiplied by $26 for 1 hour. That's going to cancel out the hours. 1 times 26 is going to be $26. In 1 hour, they earn $26. Or you could just read it, it's $26 per hour. What is this rate in hours per dollar? Okay, so hours per dollar is the same as, is similar to dollars per hour. What we're doing is we're saying, well, if I'm making $26, right? $26 for 1 hour. Let's say if I have 1 hour, right? How many $26 can go into that hour? So I go 1 divided by 26 means I get 0.03, right? Or 0.04, pardon me, 0.04 hours per dollar. Now, that would not be very useful, but you can actually multiply that by 60. If you convert that to multiply that by 60, it actually comes out to be $2.3 per minute. That might be more useful. It might be more useful in converting into minutes per dollar. So how many minutes? So if I give you $1, that person will work for 2.3 minutes and then they'll stop. So that's how you can convert one to the other. You just flip the order. Now, how long will it take them to earn $60? And that's the, I've exceeded my time, but I'm going to finish this slide off and then I'm going to dismiss you guys. If you want to leave though, I understand. But we're going to finish this off. If I give them $60, how is it going to work here? Well, this is a bit different. You want to know how many $26 fit into 60. So instead of going multiplying by 26 times now, you're going to divide by $26 for 1 hour. Because you want to know how many of these $26 fit into 60. That's going to be the same as saying 60 divided by 26, which is going to give you 2.3. So it's going to take you 2.3 hours. You could also think about this as being 60 times 1 over 26. And because these are both dollars, they cancel. And that leaves you with whatever answer comes out in hours. Now the last one was, how long will it take them to earn $1? Again, it's the same thing. 1 divided by $26 per hour. You want to know how many $26 go into here so that you can understand it. This time it's going to be less than 1. Get this, it is less than 1. It comes out to be 0.04 because we've already calculated that. 0.04 hours. And it's important to understand what's going on here. So if I have an amount of time, let me just break this up into different color. If I have an amount of time, I just multiply it and the hours cancel out and that gives me an amount of money. If I have an amount of time, what I do is instead I divide it and then that will give me an answer in the amount of money, because ultimately what I do is I cancel out this money term. And that's going to be really important. And then you can actually combine these ideas. I'm going to keep talking. I'm not sure if there's anyone left. Is there anyone even still here? Holy crap, half the class is still here. You can actually use this idea to sort of explore stuff with both of the ideas combined. 1 parsec is 3.09, so you can actually write 3.09 times 10 to the power of 16 meters per parsec. So once you know that you can convert this information into that, you can then say, well, if I've got this, I want to figure out how many parsecs. So that means I want the number on the bottom. So I'm going to go 1.89 times 10 to the power of 21 divided by 3.09 times 10 to the power of 16, because that's the same as flipping this upside down. The meters are going to cancel, and then that's going to give you the amount of parsecs, and that's again measurement of distance and stuff like that. I'm going to wrap this up here, ladies and gents. I've gone way over time. I appreciate everyone here for sticking around, even though you didn't have to. I'm going to wish you guys a safe holidays, and I will see you guys when you come back term 4, either online or sorry, I do this, just people leave, but that's fine. It doesn't matter. If I quickly look at this, by the way, finishing this off, this is going to be 1.89 times 10 to the power of 21 multiplied by 1 parsec over 3.09 times 10 to the power of 16 meters. The meters are going to cancel, which is just going to give me an answer in parsecs. So if I do that really quickly, 1.89 times 10 to the power of 21 divided by 3.09 times 3.09 times 10 to the power of 16. That's going to give me, it should come out to be about 611, so 61,065 parsecs. It's a pretty big number. Now, going back to the slide that I skipped, which was this one here, just some quick little facts here. These two numbers, you can't subtract them because they've got different sizes. It's like we'd be trying to compare it, because even though they look like, oh, you could just subtract them, you can't actually do that. Now, normally what I would say is just put this in the calculator, but there is one extra cheat that I wanted to show you. This is times 10 to the power of 21, which means you're multiplying by 10 21 times. What if you change this to 24 multiplied by 10 to the power of 20? We took away one of these 10s and we changed this number to 24. Now, this is no longer scientific notation. But what if I change this again? What if I change this to 240? I got rid of another one. And then I make this times 10 to the power of 19. Well, what you can see now is that now these are the same power. So that means you can add them and subtract them. So you can now go, well, that's going to become 240 minus 1.61. That's going to be 9. That's going to be 3, because it's going to be 9. That's going to become 8. And then, yeah, you've got 248.39. So the answer becomes 248 times 2.48 times 10 to the power of, and I've rounded it because it just dropped this stuff at the end. It doesn't matter too much. Times 10 to the power of 19, or 248, sorry. And that becomes later 2.48. 2.38. Oh my God, what am I doing? What am I doing? I forgot my 2.38, which is going to become 2.38 times 10 to the power of 21 once I move that decimal point back. So that's actually a quick little technique that you can use. And the power of this is it shows that it gives you guys a way that you can approach these. Even though they're completely different, you can still sort of multiply them, or you can still sort of manipulate them. Obviously, you wouldn't be doing something like that if you had like 2.6 times 10 to the power of 21, and then you had 3.2 times 10 to the power of 10, because that's going to be such a big change that would be not useful. But for this one here, you can sort of do it. In fact, though, if you were to subtract these two or add them, because this is such a big difference, it's probably going to be closer to this number anyway. So you could just say, well, we're just going to leave it at 2.6 because you're not actually removing that much. The multiply and divide example here I wanted to show you is when you're multiplying things, guess what? It's even easier. You don't even need to worry about it. You can just add these powers together. So that's how it works. If this is times 10 times 10, and this is times 10 times 10 times 10, the answer is going to be times 10 to the power of 5. And then you would just go, oh, there's a question. Oh my God, people are still here. One person's still here. Yeah, times 10 to the power of 5. Yeah. Is it just Sunny? Are you the only person listening? It's just Sunny. That's all right, Sunny. I'm going to be finished really soon here. So then you would go. Then you would have to do 2.4 times 3.61. You could do this manually. It's going to be a pain in the butt. 361 times 24. You multiply 4 times 6 is 24. 3 times 4 is 12. Plus 2 is 14. You've got 2 times 1 is 2. So you get a 0 here. 2 times 1 is 2. 2 times 6 is 12. Carry the 1. 2 times 3 is 6. 2 times 7. 8, 6, 6, 4. You got 2, 1. It's going to be 3 decimal points. 8.664 times 10 to the power 5. Done. You can do this. The last one I had to show was this one, 8.1 times 10 to the power 5. This one, again, you would just have this one I put up here as a bit of a novelty, but we can still do this one anyway. Let's do this. That's going to cancel 10 to the power 5. 5 take away 3 is 2, so you're going to have 8.1 divided by 9 times 10 to the power 2. 8.1 divided by 9. How many 9s go into 80? How many 9s go into 81? 9. We actually end up with 0.9 times 10 to the power 2, or 0.9 times all we have, because it's 9 times 10 to the power 1, or just 90. And that's an interesting sort of way you could do that one. But that's it. That's all the stuff that I didn't cover because I was in a bit of a rush. I can't believe, Sonny, that you stuck around for that. I appreciate the company. But I'm going to end this lesson now. At what's